In 1054 AD, a small group of children in a village in China stopped their play to gaze up in the sky at what appeared to be a gigantic star in broad daylight. They didn't know it, but this was the supernova that gave rise to the Crab Nebula, and it remained visible in the daytime for nearly a month before finally fading away. Even the smartest astronomer in those days could not have explained to those kids what they were looking at. But you're in luck. Nowadays, just about anyone can explain it to you, including me. Here's the deal. Stars start their lives chowing down on hydrogen, the universe's most abundant ingredient. Deep in the core of a star, it's millions of times hotter and more pressurized than the hottest, most pressurized pressure cooker. This is the perfect setup for nuclear fusion, where hydrogen atoms smash together so hard they become helium. Helium happens to be lighter than 2 hydrogen atoms, so you might wonder where the extra mass went. Well, it became energy, and lots of it, because as Albert Einstein's E equals mc squared equation tells us, the energy released is equal to the mass times the speed of light, which is a pretty big number. And let's just say a lot of hydrogen atoms are getting smashed. This energy is what makes stars shine and fight gravity's relentless urge to squish them into nothingness. The result, a cosmic game of tug-of-war that can last billions of years for stars like our sun, or just a few million years for the big, beefy stars that burn fuel like there's no tomorrow, which for them, there soon isn't. When the hydrogen runs out, the star panics a bit. Gravity starts winning, squeezing the core tighter and heating things up to temperatures that would make a volcano feel like an ice cube. This extra heat gets the star to say, "Fine, I'll burn helium." Helium fusion kicks in, making carbon and oxygen in the process. The star is back in the game, but this phase is short-lived. It's the cosmic equivalent of a YouTube short, lasting only a few 100,000 years for big stars. Once the helium is toast, the star starts fusing carbon, then oxygen, then silicon. Each phase gets shorter and shorter. Carbon fusion lasts about 1,000 years, oxygen fusion lasts a few months, and silicon fusion is over in a day or two. At this point, the star is like a desperate steamship captain, throwing the ship's furniture and anything else that will burn into the furnace. But when it gets to iron, everything comes to a screeching halt. Here's the problem. Fusing iron doesn't release energy. In fact, it sucks up energy. Without energy to counteract it, gravity goes wild, smashing the core into a dense, hot mess in less than a second. This sudden collapse sends out a massive shockwave, and boom, the outer layers explode in a glorious supernova. It's so bright it can outshine an entire galaxy for weeks. Talk about a diva exit. What's left? In the case of really big stars, a black hole. In the case of the Crab Nebula, a neutron star with a nebula. The neutron star is basically a cosmic bowling ball, the size of a city, and so dense that 1 teaspoon of it would weigh 1 billion tons on Earth. You're watching a video zooming into the nebula, and now you're seeing what its visible light looks like. In a mosaic assembled from 24 photos taken over 3 months by the Hubble telescope. And finally, here's a video composite from 5 different observatories, each showing a different kind of radiation. The takeaway? Stars spend their lives juggling hydrogen and helium, building heavier elements until iron ruins the party. Then gravity takes over, and the star's death is an explosion so epic that it scatters the building blocks of life, including the atoms in your body, all across the universe. So next time you look at the night sky, remember, those twinkling stars are working hard to cook up the elements that make up everything, including you. Now that's star power.